So looking at number 3 on page 53, it says find and investigate the critical points of the function f of xy equals y squared minus x squared. Okay, so the first thing that we would want to at least consider is whether or not the function is continuous, differentiable. It's polynomial in nature, so we're looking at something that's not going to have undefined values or imaginary. So we're not worried about that. So we could just hop into the first derivative, first order partial with respect to x, which would be negative 2x. First order partial with respect to y, which would be 2y. We would set each of these equal to 0. There's no way they could be equal to each other except to create a relationship, which we could investigate. All right, if I set negative 2x equal to 0, I get x equals 0. If I set 2y equals 0, I get y equals 0. And then the only thing that we could actually do is just verify that that would be true if we set f sub x and f sub y equal to one another. So negative 2x equals 2y. We're also not concerned with, because the other way to find a critical value would be to set it equal to some undefined value. Irrelevant here because there's no instance in which it would be undefined. Okay, so if I replace the x with a 0 and replace the y with a 0, I get a true sentence. So that checks out. So we're good there. So we now have, well, I guess the knowledge that the critical value is 0, 0. All right. So now using an algebraic technique, analytic technique, we want to verify or at least determine what's going on at that critical value. All right. So based on the diagram, it looks like it's probably a saddle point based on the fact that I highlighted the saddle part of the graph. It looks like, the kind of saddle that one would put on a horse. So that's the assumption I have going in, but let's see how it plays out. So let's find f sub x, which is negative 2, f sub y, which is a positive 2, and f sub xy. All right, so the second order mixed partial, taking my first derivative with respect to x and differentiating it with respect to y would give me a 0. Going the other way, f sub yx, just as a way of verifying, f sub yx and f sub xy, because it's continuous, would be the same thing, would both be 0, and that does play out. So now what I can do is find my discriminant, which is the product of these two values, negative 2 times 2 minus the second order mixed partial squared. All right, so we're looking at a negative 4. That's what the discriminant would be for all values of x and y, even the case where it's equal to 0, 0, right, the xy values. All right, so we're concerned with two things. We're concerned with the sign, S-I-G-N sign, of the discriminant, and we're concerned with the sign of, if necessary, the second order partial with respect to x. All right, so in this case, we never get past the discriminant sign because since d is less than 0, there is a saddle point at 0, 0, turns out it's 0 because f of x comma y, f of 0, 0 would be equal to 0 squared minus 0 squared, result 0. So 0, 0, 0. All right, now if the discriminant was positive or equal to 0, then it would be a different story. Well, if it was equal to 0, if the discriminant was equal to 0, then it would be inconclusive. But if it was positive, then we would look to our f sub xx to determine whether it was a local max or min.